This video will be going over the code and how to go about calibrating your electric vehicle champion kit. The list of materials and access to all other guides and helpful diagrams can be found on our website under the kit instructions page, which is linked in the description below. So the first part of this video, I'm going to be going over the test code or the sample code we have on our website. Now before I get really deep into the code, I just want to emphasize a couple things here. According to the rules clarification from the previous years, competitors aren't allowed to straight up copy code from kit providers. But the reason I'm providing this code here is just to give you a little bit of an idea on how you could potentially approach coding your vehicle. And again, you can find all this code on our website. Now another thing here is this code isn't perfect, but there aren't any bugs that I was able to find during testing of our vehicles here. But I will be going over some key points on areas you could consider improving and some other ways you can go about approaching code than what I have here. Alright, so getting into the code. The first 6 lines are just the main libraries that we need to include for the vehicle to run properly. The main 2 I want to highlight to you are the Liquid Crystal and the RoboJax BTS7960 library. The Liquid Crystal library is really integral in making sure that we're able to properly control everything that gets put on our LCD screen. And the RoboJax library is really integral in making sure that controlling the motor output using the motor driver is very simple and easy. Now, while all these other libraries are able to be downloaded directly through the Arduino IDE platform, the RoboJax library is actually a little bit unique where you have to download it as a zip file. And we have that zip file on our website, so you just have to download that zip file and add it as a library using the option on the Arduino IDE. So underneath our libraries, we are just setting up our LCD, so we're just defining it as a 16 by 2 LCD. Then we are defining our pins on our Arduino that correspond to the right and left motor driver pins. And if you are going to make your own code, I would not recommend changing any of these numbers here because they do correspond to the pins on the Arduino Uno from our PCB. And then we have the clockwise and counterclockwise and debug, and those are all coming straight out of our RoboJax BTS7960 example. And then we are just defining our motor as motor. Then we're also defining the encoder pins, so encoder A and encoder B refer to that main encoder attached to the front axle, and dial CK and dial DT refer to the encoder that is on the button's PCB. Now we're defining our push buttons, and again we have our start button, set button, and you'll notice the dial button pin. So that dial button pin is actually the encoder. The encoder, you can actually press that down, and that can act as a push button as well. You'll also notice that it's being defined as A0. That is correct because we are using the analog 0 pin on our Arduino Uno to control that dial push button function. And now we're going to define some encoder variables. So we have counter and temp. Those 2 variables are going to be we are going to be inserting the value on our encoder and using that to check if our vehicle is at the right spot. Below that we have our LCD variables, so we have a variable called position, a variable called increment, and a variable called set. So position is referring to our rotation in our sort of sliding scale of increments that we can use to adjust our target time and target distance. Increment is the amount or the value that we are actually changing our target distance or target time by, and set is just allowing us to cycle through different options to make sure that we can actually set our target distance, then set our target time, and then actually run that code. Below that we have our movement variables, so of course we have our target distance, which is in meters, target distance in centimeters, and the reason we're using target distance in centimeters as well is just it makes things a lot easier mathematically in our code. Then we have the arc length.
So arc length is the actual distance traveled of the vehicle, right? You're not actually traveling 10 meters when you have a target distance of 10 meters. You're traveling in an arc, which is a little bit more than that. So later on we have a function to calculate what that actual arc length is. Then we have our target time to set to 20. Our wheel diameter, this should be constant for everyone. We are all using hopefully the 2.875 inch T61 wheels, so those have a diameter of about 7.3 centimeters. Then we have our wheel circumference, which again is just, calculating that. And then we have our slowdown distance, snail distance, and pulse per rev. So slowdown distance is the distance when we are trying to stop, which we'll go over later. Snail distance is after that initial stop, we'll do a couple other things to get to that target distance and also make sure we reach our target time. And all that will be discussed later in this video. Pulses per revolution is something that may vary for you. This is the pulses of the encoder per rotation. So the encoder I was using had a pulses per revolution of 1200. I would suspect a lot of you will either have 1200 or 600, but again, important to check, which we'll be going over later as well. Then we just have our booleans to cycle through different actions in our code. So we have a start button pressed boolean, a moved, slowed, snail, and reached target distance boolean. Then we're just defining our encoder values, and then some other values we'll be going over later. And then finally, we are just going to be defining some timer values or variables that we're going to be using to track where we are in our target time wise and where we need to be in order to reach our target time. And now we are going into the setup portion of our Arduino code, and a lot of this is just redefining variables and making sure everything's okay. So the first thing we're doing is we're just setting up our serial monitor. So we're beginning that, and then we're entering, just a couple things that you can check when you're uploading the code, and all this should show up so you can make sure everything is actually happening properly. Then we're just starting our motor, redefining our LCD variables, and printing target distance and increment on there. Then we're also just setting up our set button pin, so we're making sure that our set button pin is defined as an input, and making sure that it is set as high. Then we're doing the same with the start button pin. And now we're also making sure that our LCD buttons are set as input and input as high. And for the encoder ones, you just want to bring your attention to the attached interrupt. So we have two interrupts, for rising, we have two interrupts that are going to be making sure that we are always changing our encoder value as we're also running a whole bunch of other functions. Right? If you don't use any interrupts, your encoder will only be, you'll only ever be tracking the encoder when nothing else is going on. So we're using interrupts to make sure we're tracking the encoder while also executing other portions of the code. Underneath that, we're just putting some max encoder values, and then we're just putting a regular, just to make sure our get encoder value function is working into that target encoder value. We have a max encoder value just in case, for whatever reason, your encoder, or your vehicle goes backwards at the start of the run. The whole thing doesn't, when you're pressing a start button, the whole thing doesn't, the Arduino doesn't get confused. And underneath that, we're just resetting all of our booleans. Alright, so now we are in the main loop function of our Arduino code. And right when you turn on your Arduino, you'll be in the set 0 portion of this loop. Now, the set 0 setting is basically the portion of the code that allows us to change our target distance using the buttons and the LCD on the vehicle. The first thing you see in that set 0 loop is that if we press that set button, then we can run this whole other code and go to the next step, the next set loop, right? So if we press that set button, that means we've confirmed that the value on the screen is the target distance we are actually aiming for. So we're just going to print set pressed, so we know on the serial monitor, like if you have it plugged in, you can check that the set button is actually working. Then we're just making sure that we are setting our target distance centimeter value to the actual target distance. We're getting the actual arc length, and we're setting the slowdown distance we need. And then we're going to print that arc length to make sure that just to make sure that we are actually getting a reasonable value that you would expect. And then we're going to get our encoder values. So the encoder value for the target distance, the encoder value for the slowdown distance, and we're going to get the encoder value for that max, the max value you'd ever want to see on your encoder during this run. Then we're just going to print out those values to make sure that we are actually getting them. And then we are going to print target time and set our increments and positions, and then move on to set 1. So set 0 again is controlling or making sure we can modify our target distances using the LCD and the buttons, and set 1 is going to be controlling the target time and not the target distance. So now, like I mentioned earlier when we were talking about the variables, we are actually going to be cycling through a bunch of different options for increments using the position variable. So we start off at position 1, and at position 1 we have an increment of 1, so we can change our distance by 1 meter. Then if we go to position 2, we can change it by half a meter, position 3 by 0.1 meters, position 4 by 0.01 meters, and if we go to position 5, we can change it by 0.01 meters, so 0.1 centimeters. So what you'll notice here is that we're pretty much just repeating the same amount of code and doing, just changing the increment here. If you were to make your own code, this is something that you could probably simplify and call a unique change you've made from the code I've created. One thing I do want to highlight here is that we do have a delay within each position change. The reason that we have this delay here is so that when you press down on the encoder on the button's PCB, it doesn't register 2 pushes of that button. It only registers 1 every time. And this next set of code is essentially making sure that when we turn the encoder on the button's PCB, we are either making sure we are adding our increment to the target distance or subtracting the increment from the target distance. And below that you can see the beginning of our set1 function. And again, like I mentioned, the first thing, or right under that, like I mentioned, the set1 portion of the code is controlling the target distance. And you can see the first thing, just like with the set0 code, is what happens if we press the set button. So if we press the set button, again, just like with the set0 code, if we press that set button, it means we want to lock in that target distance. So we're done. Now we're just going to go to the main code. So we're going to make sure we print our target distance and print our target time so we can make sure we have the correct values before we run our code. And just like with the set0 code, we're doing the same thing here. We're cycling through a bunch of positions and a bunch of increments to allow you to adjust your target time. And again, if you were to make your own code, which you are supposed to be doing, this is something you would want to, you could potentially simplify. And this is just the bottom half of that set1 portion of the code, which is exactly the same as the set0 portion. And now we are in the set2 portion of the code, which is where we're actually going to be running our vehicle. Now the first thing you'll see here is if we press that set button again, we can go back to set0 and change our target distance and run through that whole cycle again. Underneath that, we have what happens if we press our start button. So if the start button is pressed, then we're just resetting all of our variables, we're resetting our counter, we're getting the time we started, we press this button, and then we are just going to turn our start button press variable to true to move on to the next section of code. Alright, so now that the SB pressed boolean has been turned to true, we are in this section of code. And in this section of code, we're really just turning the motor on. We're running the motor at 50% speed. Now you don't need to run it at 100% speed, obviously, because the target times are only between 10 and 20 seconds. So 50% and less, or a little bit more, is more than enough to reach those target times. Underneath that, we now enter the moved function after we turn the motor on. And in this section of code, we're just continuously checking that counter until it reaches the desired slowed down encoder value. And once we reach that value, we can, stop the car initially. So we're spinning the motor backwards to make sure our car is stopped, and then we're just going to turn off the motor. And then we are checking our time, where we are at currently, and the difference of that time to our target time. And then we enter the slowed function of the code. So this section of code is really where you can start to differentiate yourself from the code I've made here. So just to explain what we're going to be doing here, essentially we're just going to do a quick set of pulses at a set speed and a set delay between those pulses. We're going to do 5 of those. We're going to take the average of them to get a good idea of how far we are going per pulse. Then we're going to go and we're going to determine how many pulses we need to get to our target distance and the delay between those pulses in order to reach the target time. With this strategy, we've been able to get target times within 0.5 to 0.3 seconds every single time. The main downfall with this method here is you really have to trust that these pulses are very accurate. So there is a little bit of concern with the target distance if you approach it this way. Another way to approach this is that you could track the actual distance you're traveling, at a specific amount of pulses. Or there are a lot of other ways to do this as well. You can also try, instead of doing this pulse strategy, you can come up with an equation on how different speeds correlate with, or how different motor powers, which if you recall we started the motor at 50% power, how 40% power or 30% power and so on and so forth correlates with time to 7 meters, and then generate an equation that uses target distance as uses the target distance as the x value and the percent motor speed as the y value. But here I'm just going to be going over the code I have. So again, we're just going to run 5 pulses where we are just rotating our motor at 10% speed for 0.2 seconds, stopping the motor, waiting 2 seconds, and then we are just getting that encoder change. Then we're getting the average of that encoder change, and we are just rechecking our time. In the Snail portion of the code, we are actually going to be running those pulses at the desired delays. So again, this first set of code is just determining how many pulses we need to reach our target distance, and then determining how much of a delay we actually need to reach our target time. This section of code is just initiating those pulses, and then we are just getting our final time, which is when we have reached our target distance. Now, the last portion of this set 2 portion of the code is the reach target distance, and here we are just outputting the actual distance we traveled and the actual runtime of that run. And using this information, you can make changes to the inputs of your target time and target distance to make sure your second run is better than the first. And then we reset all of our booleans and the counter. And then these are just some supplemental functions we used during the other portion of the code. We have AI0 and AI1. Those are the interrupts. So these functions are running whenever a change is every time a new pulse is read from that encoder. So AI0 is going to increase the value of the counter, and AI1 is going to decrease that value. Then we get to the getEncoder function. This is just converting our target distances to the actual encoder value corresponding to it. And then we have getArcLength, which uses this function to determine the ideal arc length based on a given target distance. Now this assumes that you have a perfect arc, which is another potential flaw of this code here. So the vehicle width is roughly 13 centimeters, and so we're assuming we are using a can distance of 15 centimeters. So then we are determining our arc height as 1 meter minus that 15 centimeters, and then we are getting the arc radius, the arc angle, and ultimately the arc length, and then returning that arc length, which again is that ideal arc from the start point to the target distance. So this is the encoder calibration code, and essentially what you want to be doing here is you want to upload this code to your electric vehicle, and then open up the serial monitor. Then with the code running, you want to rotate the front wheel, one of the front wheels of that front axle in one full rotation. So you can see me doing that here. And after that, you want to refer to the serial monitor. You should, get a number value, a whole number value ideally. For me, that number was 1200. So that may be different for you. I wouldn't trust the manufacturer's pulses per revolution because mine said 600, and again I got 1200 as the actual pulses per revolution, which is great, but again something you want to verify. Another thing you want to verify here is that when you're rotating that wheel forward, that the counter value is actually increasing and not decreasing. If that counter value is decreasing, then I want you to unscrew the encoder A and encoder B wires attached to the Arduino Uno and switch them. So switch that wire that's plugged into the encoder A terminal to the encoder B terminal, and the wire plugged into the encoder B terminal into the encoder A terminal. For the main calibration of the vehicle, the first thing you want to do is actually set your target distance. And again, you can press down on that encoder dial to change your increments, and when you want to lock in that target distance, press that set button. And now the same thing here with that target time. When you want to lock it in, you can press that set button. When you're at this screen, if you press that start button, your vehicle will run, so just be very cautious of that. Before you do any testing, you also want to make sure you have a track set up, and you also want to make sure that in the middle of the track you have the tape set up for the cans. You don't actually have to test with the cans, or you're doing it for practice, especially when you're at the very early stages of testing. But it is very helpful to make sure that you do have at least the tape markings, so you have a good idea of if your curve is correct and what changes you need to make. Now we can set up our target block. Now a target block essentially is just something you can stand up at that target point so you can aim towards. Here I'm using just two pieces of wood that were screwed together, and I have a line in the middle. So when I'm at the when I'm at the starting point, with the vehicle, I can use the scope on the vehicle to aim to the line on the target point, or excuse me, on the target block. Now, for your first run, you won't have any idea of where the true aiming of your vehicle is, but a good, just a good frame of reference when you're aiming your vehicle. Set that target block at least 1 meter to the left of that target point. It's a little difficult to see on this image here, but essentially what you want to do is just look through the scope on the vehicle and aim towards that target block. Before you run your vehicle, I want you to take note of one specific thing while it's doing its run. You want to make sure you take note of whether your vehicle is to the right or to the left of where the outer can should be, or in other words, if your car is undershooting the curve or overshooting the curve. So this is the vehicle at the target distance. I was aiming for 7 here. So again, we made note that the vehicle during this run was to the right of the can, and now it is to the left of the target distance. So from this point, with the code, the example code I have, this distance will only, the front to back distance will only ever be perfect if the arc of the vehicle, the arc, the curve set by the caliper is correct, because it goes until it reaches the ideal, the ideal arc length we calculated previously. So to make things a little bit easier for you to understand, if you need to increase or decrease the curve, is you would first adjust the position of the aiming block until you get an aiming at the specific curve value that lines up with that target distance. And from there, you can determine again, is my vehicle to the right or to the left of of where the outer can would be. And if it's to the right of the outer can, that means you're not curving enough. So you would have to pull back the caliper to make sure the front axle is steered more to the right. And if it was to the left of where the outer can should be, you would have to decrease the value on the caliper to decrease the steering angle of the front axle. So quick recap here. If your vehicle is to the right of where the outer can should be and is to the left of the target distance, you would first try to decrease your aiming and then increase your curve to reach the target distance. Now, if again your vehicle is to the right of the outer, where the outer can would be, and is to the right of the target distance, you would first try to increase where that target block is, so make it more to the right before you go and adjust the curve. And again, if you ran it again and the aiming was good but it was still to the right of the can, you could increase that caliper position to reach the target distance. Please take note that the order of priority here is to make sure you have your aiming block in a decent position before you go and wildly change around that caliper position. Because it may seem like, your caliper is off, but maybe it's just your aiming. And it's much easier to change the position of that block than it is to get a very precise position on that caliper. Alright, so another scenario here, we have our vehicle that during the run it was to the left of where the outer can would be, and at the end of the run it was also to the left of the target point. So the first thing we want to do is we want to decrease our aiming. So because our aiming block is on the left, we want to move it to the right. And we want to move it, we want to keep moving it until it, has an aiming that is relatively consistent with our target distance. And then we can run it again and determine, is it still to the right of the target can or still too much to the left of where that outer can would be, not target can, where that outer can would be. Still too far to the right or too far to the left. And if it's too far to the right of the can, we can increase our curve or increase our caliper setting. And if it's too far to the left of the can, then we can decrease our caliper setting. One last scenario here. So let's say again you ran your vehicle and it was again to the right, to the left of where the outer can would be, and it was also to the right of the target distance. So again, first order of operations here, we want to increase our aiming so we can reach that target distance. So we are going to move our aiming block more to the left until we get a vehicle aiming that is consistent to where that target point is. Then again, we can reassess. Is the vehicle still too far to the right of where the outer can would be, or still too far to the left? If it is still too far to the right, then we can increase the curve and try again. And if it is still too far to the left, we can decrease our curve and run it again. If you're continuing to get, super inaccurate and inconsistent results, it may be worthwhile to go ahead and look at this section of code if this is something you're implementing in yours, to see if we can, increase the amount of pulses and make them have a shorter duration. So essentially here, instead of running these pulses for 0.2 seconds, we can run them for 0.1 seconds. And we can, instead of running them at 10% power, we can run them at 5% power. We can even run more than 5 pulses so that it's a larger sample size to compare each pulse to, so that after we run these pulses, we can then get a more accurate understanding of how many pulses we need to reach our target distance, and then using that knowledge to get a better assessment of the delay between those pulses to reach our target distance. And if you do end up making any changes, you'll want to also make sure you're adjusting the pulse time in the Snail section of the code, and also make sure that you're adjusting the pulse duration in the initiate pulses for loop. One thing you want to take note of, especially during a competition, is the final distance and final time that is outputted on your LCD after the run. Now, what you don't necessarily want to focus too much on this data when you're when you're practicing at home, because you like everything to be perfect for distance and perfect for time by the time you get to competition. but when you're actually at the competition, this sort of data helps you, right? So if you get this data back, you can verify, does the event supervisor, did they get the same time as what my LCD is getting? And if not, you can adjust your target time to correct that difference. Another thing with the final distance, if your run is saying it got 7 meters, but maybe it actually got 3 centimeters less, you can adjust the target distance, or you can increase the target distance by 3 centimeters when you go to set up your next run to account for that difference as well. One final thing to consider, and this is really only pertinent to testing 20 seconds at 7 meters, is the delay between the pulses. Now, I personally haven't seen any, or haven't gotten any runs with pulses longer than 3 seconds. But if for whatever reason, you are noticing your pulses are going longer than 3 seconds, you definitely need to make some changes because your run will be stopped if your vehicle stops moving for over 3 seconds. But with all that being said, thank you for watching. Feel free to leave any questions in the comments or send us an email. Stay unfazed.